Okay, so now remember that we looked at the common source, right? And I only looked at the small signal picture, and I'm sure you know that I cannot, or first let me ask you, can I connect the small signal directly to the gate of the transistor and expect the transistor to work? So what should I do? Should bias it. So let us say I have a small signal voltage source, and let us say DC bias VB. How do you connect the two now? I have to couple the two so that at the gate I have DC voltage plus AC signal. What do you do? Yeah, again, simplest way is to think of it like this. Maybe the signal source has a source resistance, doesn't matter. So you cannot connect this directly. You have to add a DC voltage. So assume that you are putting an ideal voltage source with a value of the required VB, but you can't use a voltage source. So what do you use? A capacitor with a very large value, right? And of course you have to make sure that the capacitor is charged to that required VB. I have the grounded voltage source VB. What do you do? Yeah, can I connect it directly like this? Why not? Then the voltage across the gate will be fixed to VB. That's exactly the opposite of what you wanted. So you put a large resistor RB here and couple. And let's say here I have the PMOS transistor connected to some bias voltage acting like a current source. Connected to Similarly, at the output, we saw I cannot connect the load to ground, DC ground. So how do I connect the load here? How do you put it? How do you connect these two now? Again, I mean, what is the problem if I connect it directly? Yeah, this will draw a DC operating point current and screw up your biasing point. So you need to make sure no DC current flows through this path. So what do you put for that? You put a capacitor, because you know in steady state DC current flowing through capacitor is 0. So let me call this CB1, CB2. So this is how you do, you know, this AC coupling and do it. And as we saw, I mean, instead of using a different voltage source VB, I can derive this by putting a resistive divider from VDD. That's okay. Now the point I want to make is the following. Again, as I mentioned before, so what can you say about the values of the capacitors first of all? Do you think there will be small capacitors or large capacitors? Really large. On chip it is difficult to have such large capacitors. So typically we try to avoid doing it. So usually this AC coupling is done off chip. So maybe on the PCB on which you have your IC, you do this AC coupling and then provide the signal to the chip so that the amplifier is happy here. And let's say you want to give this to a second stage of analog circuitry. You once again don't do this fellow. You try to directly connect it. And remember, the output here will have a DC part and a signal part. You design the circuit so that the DC at the output of the first stage is compatible at the input of my second stage, so that you can avoid kind of, you know, decoupling the DC, adding a different DC and stuff. But of course off chip you have to do something like this to couple the signal. So now remember, when I looked at the frequency response of the common source, I only considered these capacitors C1, C and C2. Correct? Yeah.
Output also gets connected to off-chip capacitor.
Yeah, I mean what I'm saying is the final load, right? I mean that is going to be outside the, yeah, good question, I should have mentioned. Let's say you do all the processing and finally you have something, you probably might want to do something like this.
Not in between, like between two amplifiers.
No, you don't do it. I mean the idea is you can't have a really large capacitor on chip. You try avoiding it. I mean I'm not saying it is not at all done. Sometimes it is done, but generally it is not something that you want to do. Especially if you are working at low frequencies, the capacitance value you want to use might become really, really large. It is impractical. If you are looking at gigahertz frequencies, yeah, I mean the capacitance required might be not so large. Okay, so yeah, the point I wanted to make is the following. We considered only these three capacitors when we looked at the frequency response. But let us say you do this. Let us say you make only a simple common source amplifier on chip. Off the chip you have these fellows here. You have an extra capacitor CB1 and CB2 here. So they will also obviously contribute to poles and zeros. So let's try to see what will be their effect. Let me erase this. Let me quickly draw the small signal part alone. So supply VDD is grounded. The bias voltage is also grounded for small signals. This is also grounded. Great. Now we already know that the capacitors CB1 and CB2, they will be very small or very large. They actually will be really large compared to the parasitic capacitors you have. Correct? To give some numbers, parasitic caps might be in the order of few femtofarads. These may be in the order of nanofarads or microfarads off chip. So no comparison between these two. So which means if I do the experiment where I try to increase the frequency from S equal to 0, at S equal to 0, which is DC, what can you say about all capacitors? They are all open. Now if I keep increasing frequency, which capacitors here will start to not act like an open circuit? CB1 and CB2. At those frequencies, what can you say about these? Yeah, at those frequencies where these fellows are not acting like an open circuit, these will still be acting like an open circuit. So which means at very low frequencies, I will not consider them. So I will say at low frequencies, I will consider only CB1 and CB2, which means I will consider all the other capacitors, so C1, C2 or whatever you have, to be 0. And this is a good approximation to make because I know the capacitors are going to be really large. So if I were to find the poles due to these capacitors, they will be at a low frequency or high frequency. The capacitance are really large. So the pole you compute for these capacitors will be at a very low frequency. Okay. So first tell me, because of these two capacitors alone, how many poles I'll have? 2 poles, because I can initialize the voltage across both capacitors without issues. So again, for pole location, the input output locations don't matter, so I'll null the input. Now when can I write the pole locations as 1 by R times C? If the poles are capacitors are uncoupled, do you think the capacitors here are uncoupled? What is the resistance seen by CB1? RS plus. Do you think that will change if I open or short CB2? So which means this is an isolated RC section. This will result in a pole at what location? 1 by CB1 times. Similarly, now I have an isolated RC section at the output side. What is the effective resistance seen by CB2? To the right side I have RL. To the left side, what is the resistance? Yeah, I mean, okay, let's call this MP and MN, NMOS and PMOS. What is it? The resistance here, I have two components. Looking up, I'm looking into the drain of the PMOS transistor. Gate and source are shorted. What is the resistance? R0 of the PMOS. So I'll just mark it here. I'm looking into the drain. It is R0 of the PMOS. What can you say about the resistance looking down? Do you think that will change if I open or short CB? Maybe I'll ask the question again. I'll rephrase the question. So I'm trying to find the resistance looking down. Again, I'll apply a test voltage. Now I have this structure here, RB, CB1 and RS. I apply a small signal disturbance at the drain here, which is Vtest. What can you say about the small signal voltage at the gate? Same, Vt. 0, or it will be Vt times 1 plus 1 by Gm R0. 0? Sure? Something we discussed probably 2-3 times before also. understand the switch and the fan. So just because I apply a drain voltage here doesn't mean this will result in a gate voltage here. So this small signal gate voltage will be, so it doesn't matter what is the effect on, what is the condition on CB1. This voltage is always 0. So what is the looking down resistance here? I am looking into the drain of the transistor. We just saw gate is small signal ground. What is the looking down resistance? Is that clear? So now let's write the complete resistance. So what is the resistance seen by CB2? Okay, let's write the pole directly. It's going to be the capacitance CB2 times the resistance it sees. How much is that? Okay, let's write R0 P parallel R0 N plus. This is clear to everyone? Basically, this is connected. This is also small signal ground, and here also have the effective resistance small signal ground. So those two will be in series. So basically, I have CB2. On the right side, I have RL. Left side, I have the parallel combination of. So this is what I have, and this. And as you see, CB is going to be very large, so these will be at very low frequencies. So that's the pole. Let's look at the 0. But any confusions on how we got these? The resistance seen by CB1, CB2. Okay.
Normally you said at input low frequency pole.
I didn't hear you.
Normally you said at input side low frequency pole.
Okay. I mean okay. Let's rewind back. His question is, we just saw that at the input we have low frequency pole, but remember that was in context when I have this capacitor C. Correct. Here we are looking at much low frequencies, where these capacitors are not coming into play yet. Yeah, so now let's look at the effect of zeros. So let me copy paste this. So if I ask if the circuit has zeros, what should be the question you should ask me back? What is the input and? Yeah, so now I give you the information. This is the input. This is the output. So how will you find if you have zeros or not? I'll try to short capacitors. So can I short CB1 and will the output be non-zero? I mean, basically if I short this, do you think the output here and here will be non-zero? Non-zero? Zero or non-zero? Non-zero. So that is one pole, which means we have definitely 1 0. To check if I have 2 zeros, what should I do? I should be able to short both of them. If I short both of them, will the output be non-zero? I mean, okay, does it even make sense that I am able to short both the capacitors and the output is fine? Yes? Why? Ideally, what do you want the capacitors to behave like? A voltage circuit, I mean, ideal voltage source which should act like a proper short circuit for small signals. So it should not be surprising at all that, hey, I can short the two capacitors, I get the output. In fact, that's what you wanted. So I have 2 zeros, so we can find that. Again, I look at it this way. I already know that this RC section is uncoupled and this RC section is uncoupled. So the output side RC section is this. I'll just copy paste it. So this is the output side RC section. This is the input side RC section. So which means I can basically look at this fellow alone and see if I have a 0 here. Correct? Because this is isolated from this. Let's try to see if I have a 0. I mean, what is the location of 0? If I call this VG1 for example. So let us say now this is my input, this is the output. Because I am considering this in isolation, I want to find the location of 0. How will I find it now? What will I assume for VG1 of S? And then you just apply KCL. That's it, right? Let's apply KCL. This is the only node here, or one of the nodes here. So sum of the currents leaving that node is going to be 0. What is the current here? What is the current here? 0? 100 amps? 0? Confident? This is 0, current is 0. What about the current flowing in this branch? I mean in the direction. So basically I'm writing KCL, sum of the currents leaving the node is 0, the current flowing down is 0 plus what is this? Sorry, 0 minus V in of S by RS plus 1 by must be equal to, clear? So if you solve this, I mean simplify this, I get V in of S times SCB1 to be equal to 0. Yeah, yeah. Oh, yeah, the idea, see, I can think of it as 3 isolated transfer functions now. This is one RC section and this is one RC section. In between I have the transistor, correct? So which means if I have 2 zeros, I am basically saying that there is a 0 in this RC section, there is a 0 in this RC section. So because they are uncoupled, right? So I can treat them separately and find the 0 here and 0 here, that's all. Yeah, correct. If this voltage is 0, what can you say about V out? Right? That's the thing, right? This is the final transfer function from V in to V out is essentially product of 3 different transfer functions. One is basically of this fellow. Second is a transfer function from gate to drain here, which is Gm times R0 or whatever, times the transfer function here of this RC section. This is what I have drawn here. Right? Yeah, so this is what I get. I know for a fact that my V in of S is non-zero. So what is the possible solution? S should be 0 because my CB1 is not 0. So where is the location of 0 here? At the origin. Right? Now for this RC section, I find that the 0 is at S equal to 0. Similarly, can you take a guess as to where will be the 0 of this RC section? I mean, look at these two things. Do they look different or similar? I have 2 resistors on either ends and a capacitor in between. Just put a different makeup and it's looking different. So if here the location is location of the 0 is at S equal to 0, what will be the location of 0 here? S equal to? So you can directly write here also I'll have S equal to 0. So to summarize, what I have is the following. I have 2 zeros, both at S equal to 0, and I found that I have 2 poles. One was due to CB1, that was CB1 times I think RB plus RS, and CB2 times RL plus R0N parallel R0P. Right? So which means if I were to write the transfer function A of S, again these are at very low frequencies, right? We are looking at very, very low frequencies where the parasitic capacitors in the transistor are not coming into play. Only these capacitors are acting. So how can you write my A of S as now? I have 2 zeros at S equal to 0. So numerator should have, I'll have a DC gain A0, let's write that. And I have 2 poles, 1 plus S by P1 times. So if I were to show it clearly, let me call this as P1, this as P2. So if I try to sketch the Bode plot of this transfer function, is everyone familiar with Bode plot? Okay. Okay, how will you find Bode plot? Tell me. I give you a transfer function A of S. What is the first step you do to find the Bode plot? Corner frequencies. Okay, this is the This is a Bode plot is a plot where the x-axis is what, y-axis is what. Let's start from that. X-axis is what? Frequency. Frequency. What is the variable for the frequency? S. Omega. Fine. What is the y-axis? Magnitude. I mean, maybe in dB or anything. So which means to plot, I have A of S to plot mod A versus omega. What should I do first? I substitute S as. So now tell me, how will the Bode plot look like for this? I have a square term. Okay, everyone wrote gate, right? All of you got, all the MTechs wrote gate. All the BTechs did your control theory course E210. Tell me, how will the thing Bode plot look like? I mean, okay, at very low frequencies, right? Among these, which will dominate? S square is there, 1 plus S by P1, 1 plus S by P2. Let's say look at really low frequencies. What will dominate? S square term will dominate, correct? So how will the Bode plot look like corresponding to S square? Omega square. So how will that look like if I plot in log scale? This. I give you 3 options, okay? Option A, option B, option C, option D. Tell me. C. Okay, what will be the slope of that? Minus 40 dB, plus 40 dB per decade. So it will go something like this. Okay. Now what happens after that? I have a pole at what frequency? P1. After encountering the pole at P1, what happens to the slope? It will basically become, decrease by 20, so it will become 20 dB per decade. So this is 40 dB per decade. So, and then what will happen? Again it will encounter the second pole. I mean, this is a Bode approximation, right? I mean, this is a Bode approximation. The actual plot, basically, look at this, right? Again, this should not be surprising, because remember, we wanted to make sure that the capacitors, how do you choose the value of the capacitors actually? How do you determine what is large? Let's say I give you the minimum frequency of the signal. How do you find it? 1 by omega into the equivalent resistance seen by the capacitance, correct? So basically you want to make sure that for your signal frequencies of interest, how should the capacitor behave like? I mean, ideally, how should the capacitor behave like here? We cannot make it behave like short circuit for all frequencies. So at least for your desired frequencies of interest, it should behave like a short circuit. So which means it makes sense that you have a constant gain here for your desired frequencies. Maybe you will choose your minimum signal frequency here, or I would say for this minimum signal frequency, you would have chosen your capacitor's value so that the pole locations are here. Now if I keep increasing the frequency beyond, now the parasitic capacitors inside the transistor will come into play. So as we saw, we have those 2 poles. Now these capacitors will start to come into play. Now when these capacitors are coming into play, what can you say about CB1, CB2? They will be now short circuit. That's what you ideally wanted to behave like. So now these 2 poles come into play. So which means whatever at large frequencies you will have something. But the point I wanted to make is that if you have this AC coupling structure here, the moment you introduce one of them, you will have a 0 at S equal to 0, and you will have a pole at the 1 by RC frequency, right? So because remember, ideally I want to make sure that this capacitor acts like a short circuit for signal frequency, but I don't want any DC current to flow through the capacitor. Capacitor basically makes sure 0 DC current flows in steady state. So this basically makes sure that DC is blocked and all the other frequencies are allowed. So what we have is essentially something like this, right? So this is what you essentially have. So this will have a Bode plot like this, right? So if you find the transfer function here, what will be the transfer function here? Can you help me write the transfer function from V in to V out? Okay, it's an impedance division Tell me, write the impedance division, help me write the impedance division factor. R by, so this is SRC by, so we have a 0 at S equal to 0, and then you have the pole at 1 by RC. So basically this is essentially high pass filter which basically knocks off the DC. So that's what you want. You don't want DC current, and for all signal frequencies it should behave like a short circuit. So the point to have in mind is, anytime you have this AC coupling business, each of those capacitors will give rise to a 0 at S equal to 0, and then you have two poles to counter that, because if you didn't have those poles, the gain would just be, you know, if the poles were not there, just of course that doesn't happen. So you have a pole and a 0 associated with it. Any questions? Okay. So I'll stop here and we'll continue later. Yeah.